All right, so we have finished off our very first project, which was our sound engine. Now you can look at it from a conceptual standpoint, as our sound engine being kind of the Hello World app for making noise on your computer. We built a very, very simple framework which caused noises to be played. Now we're going to take a look at building a music engine, which Logan has described to me over and over again as the Hello World app for making music. Now, what I want to do is just kind of talk to you briefly about how this ties into the sound engine that we've already created, how the two are related, and some of the key, I want to say key concepts that are going to come up while we put the music engine together so that you're fully primed and just ready to start coding. So, for starters, we began by creating a sound engine, okay? And you guys remember this. And all those other cool diagrams that I drew in the previous videos, just imagine those all encapsulated in this little box. So here's our sound engine. Our music engine is actually going to sit outside of this. Now, Logan, you had a really cool definition for the music engine.
Well, you could say that the music engine, in this sense, is merely a system that can track events over the passage of time.
Yeah, I like that one. So really all the music engine is going to be is kind of an internal time system. It's got some other stuff too. It's aware of more than just time, but we'll get to that. So this is a timeline. Those tick marks are my timeline. And we will decide through the music engine that at various points along the timeline, an event is going to be called. So I'm going to call that event out in the form of a line, which in this case reaches out and plugs into the sound engine. It's going to, basically our music engine is going to call on parts of the sound engine.
So simply we're going to apply the music engine to the sound engine to result in the production of audible sounds.
That's really all there is to it. This music engine we're creating wouldn't necessarily have to be applied to sound. If you wanted to, you could apply it to changing colors of your desktop.
Exactly. It just so happens that we're going to calibrate it for use with common musical terms.
Right. So just to make sure everybody's totally clear, it's not like this music engine itself is going to be a freestanding work that is going to make sounds. It's actually going to leverage our sound engine to handle the playback of sound. Really all the music engine is doing is calling out events along the timeline.
Exactly.
On that note, there are some concepts that are a part of the music engine that you will have to be aware of because we're going to have to code them in. One of the more important ones is time, and we'll talk more about that here in just a second. Another one is the concept of notes. Now, I'm using the term notes loosely, and every time I say the word notes, Logan's eye twitches a little bit, because really what our music engine is doing is just calling out events.
And where we get the term notes is, again, you can say that the passage of time results in the firing of generic events. But in our case, we're going to calibrate this music engine to work in musical terms.
Right.
And therefore, it's fair to say that those events that are getting generated could be called notes.
Exactly. So it's a terminology thing. But we're going to use the rate at which these notes or events are called upon along the timeline to denote different types of notes, such as quarter notes, and eighth notes, and whole notes, and we'll talk more about that in a bit. Now, something else that is going to be covered in this project, not necessarily as a part of the engine, is the concept of note storage. And really, this is just for the sake of playing back notes that are generated.
Exactly, and part of this really ties into the whole Hello World theme, if you will, of the music engine. And this is just to prove how simplistic the data can be. We're going to create an example method for storing notes in time, so
That's
covering
right.
note storage, but we'll show how to do it with as little code as possible.
Now, there is one key concept that I want everybody to be aware of as we move forward, and really that's the basis of how we are going to be handling time, because that's the biggest thing that our music engine does, is it deals with time for us. And we want to think about time in a musical sense, which is why we're not thinking of it as just an event outputter. We're thinking of it as a musical engine, and we're thinking of those events as notes. So we've got to start thinking about music. So I'm going to try, with my limited drawing skills here, to draw a musical staff.
Good work, I must say, on the spacing.
It'll do. All right, so we're going to basically, this is considered one measure. That's all this is, one measure. And I could do the treble clef, and I'll try to give you a really lousy treble clef. So, okay, sure. Now, Another concept we have to kind of work in, just so that you understand timing in relation to music, is the idea of time signatures. Now, time signatures are one of those great things about music that can get wildly complicated, and they can take the concept of notes and start skewing them and making things very, very interesting for you as a computer person. So what we're going to do, for the sake of discussion, is just talk about time signatures in the sense of 4/4 time. Now, it's important that you know, here I'll try to break this up too. So here's where our measure actually starts, and there's all the stuff that takes place before it. And don't make fun of my treble clef because I drew it really fast. I can draw a better one, I promise. So when you see a time signature, 4/4 time is how you'll generally hear this heard. My piano teacher actually always told me that it should be read thus. It should say, when you see 4/4, it should actually read as 4 beats to the measure, and a quarter note gets 1 beat. So 4 beats to each one of these little blocks of time that you see here. We're calling this one measure. And a quarter note is going to get 1 beat. That's an important thing to keep in mind, because 4/4 time is generally considered to be common time. More music is done in 4/4 time than just about anything else, which makes it easy for us to talk about. Now, with that in mind, if we're thinking musically in terms of our timeline, now take our little music measure here and think about that continuing on over and over again, and that's going to become our timeline for our music engine. It's just this one ongoing musical staff that just continues on forever.
Exactly. Just take this as a base structure, and depending on how long you want a given piece to be, just keep repeating it.
That's right. So if you wanted to actually draw some notes on here, assuming you're drawing quarter notes, which that's where I'll start, so we'll put a little quarter note in here, and a little quarter note. I'll play the same note over and over again, because that's how boring I am. Bink. So there's 4 notes, 4 quarter notes. We now have 1 full measure. We've actually completed our time signature. Now, here's where things start to get fun. This is how you would actually compose music if you were doing it on pen and paper. And this is how it was composed for hundreds of years. Somebody would start with a piece of paper that had a staff on it, and they still do to this day. If you're composing music, this is how you do it. We don't have this luxury, because for us, this is placed kind of arbitrarily. We could really draw these notes anywhere we wanted to. If we wanted to cram all 4 of these notes on the left-hand side of the measure, it doesn't matter. They're 4 quarter notes, and 4 quarter notes is going to fill 1 measure, so it doesn't matter where they're placed. We can't do that inside the computer. We need some way to spatially represent these things in time. Now, what am I getting at? Well, basically, what we need to do is be able to take this concept, this abstract concept of a measure in time, and break it up into a concrete division of subtime units. And that's how it's got to be fed in the computer. So that a note can be played, say, at this moment in time, and at this moment in time, and then at this moment in time, and at this moment in time, just as a random example. We need some way to take this measure and quantify it into a set number.
Exactly, and that really is the goal there, is just to quantify this passage of time into a discrete number of units.
Because the computer doesn't just understand a measure. We need something that actually counts off. So what we're going to do is we're going to take our measure line here, and we're going to divide it into a set number of calculations. Now, that number of calculations is going to vary a bit as we build our engine, and that's not something I want to get into too heavily right now, at least not right this very second. What I'd like to talk about first is how notes and time are going to correspond. So you saw me just draw out 4 quarter notes. I don't know, maybe it'd be better to go ahead and go into how we're going to measure time. What do you think, Logan? You think we'll do time first? Yeah, let's do it that way.
Yeah, that sounds fine.
All right, let's just do time first before I get too far ahead of myself, because I will if I'm not careful. Now, how do we measure time in the music world?
Well, generally it's tempo.
That's right,
tempo. Which is often measured out as beats per minute.
Tempo equals beats per minute. And we are going to build a system as a part of our music engine, a metronome-style system that's going to work in exactly the same way. It's going to feed out 1 beat per minute, but in terms of the computer, you can think of this actually as an event per minute.
Exactly. If you go back to the generic side of their timing system, as far as the computer is concerned, these are just things happening. They're just events in time.
Yep. And if you wanted to take that even further, you could also say that this is just an update per minute.
That gets into exactly how we're going to realize this event. And since we're in XNA, the actual occurrence of something happening is going to be done by simply hitting the update method.
Exactly. So that's kind of going to be the crux of our timing system at first. We're just going to start off just by simply taking a BPM value, and that will control how quickly we update. But the problem with that is if you're only updating on the beats, then you can only play notes on the beats.
Exactly. Since we get back into this wonderful world of the computer where absolutely everything must be quantified and counted.
Exactly.
We have to say exactly how much space we're going to give ourselves in between beats.
Exactly. So if you've got like just kind of a representation, if these are your primary beats and you also thought of them as your primary updates, and that's all you had, then you could play a drum beat here. But what if you wanted to go do 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 do? You need some way to get some kind of division in between your primary beats. So we are going to take a look at our tempo as actually two different components. One being beats per minute, because we need beats per minute. That's how we're actually going to how do you say that? That's how we're going to march time forward based on real world time.
Exactly. Not to mention, having a metronome timed event is going to be helpful to us later if we would like to play a metronome along with any given piece of music. Also,
if you're trying to build a piece of music that's based off real-world sheet music, in a lot of cases when you get that playbook from, I don't know, from your favorite band, at the top of the musical notation, they're actually going to tell you the BPM of that particular song, so you'll have that as a basis to work from. So, of course, that's very important in terms of musical theories to have your beats per minute, but we also need this number of divisions in between each beat. So our second calculation that we're going to use in the computer is going to be ticks, or calculations, it's all on how you want to look at it, per beat.
So really what this is going to do is simply subdivide our beats per minute, meaning in actuality we're going to get a lot more update events than we are going to be getting beats.
Exactly. And you have to. Again, because really, if you look at it this way, again, as I was saying earlier, if all we had was just the beats, then we could only play drums on the beats. If you subdivided it only once, all you could do is double time. So it'd be
Exactly, but that's actually an interesting idea behind the subdivision, is every time we subdivide, the new subdivision is placed exactly centered on our original lines.
And that's a problem that we'll kind of take a look at and address a little bit later. Right now, all we're trying to do is get you down to the concepts of taking this really kind of abstract idea of musical time and quantifying it into something that a computer can understand, where we've got to take our beats per minute and then work into that our ticks per beat, allowing us to take those updates and subdivide them to the point where we can bring in some music, or we can start playing notes in during that time. Now, that's not all. So we've talked about timing to a certain degree. It's going to be beats per minute and ticks per beat. The other thing is notes. Now, this is where we're going to assign some concrete values to help us keep track of how our notes are going to be positioned. Because, again, if you think about it, if we go back to this example, let me actually move down here. So here's one beat, here's another beat, and then here's any number of ticks. And right now, let's say I don't care how many ticks there are, just
suffice to say that there's a lot of them.
Suffice to say there's a lot of them. If you take the concept of a note, now there are different kinds of notes you may be familiar with. There's a quarter note, and in 4/4 time, a quarter note gets one whole beat. There's an 8th note, there's a 16th note, a 32nd note, a 64th, even a 128th, if you can bang on the drums that fast, which I think automatically qualifies you to play in Metallica. But anyways, so there's all these different kind of notes, and those generally, inside when you're playing a musical instrument, in a lot of cases, those notes control duration, or how much time is going to pass before you hit the other note. On a drum, you have no duration. So that's something to keep in mind. We're building this whole system with the concept of drumming in mind. If you're doing it with piano, then the different types of notes control how long you're going to bang on that key. So like a whole note is going to bang out 1, 2, 3, 4 in 4/4 time, where a quarter note is going to get that full note, an 8th note's going to get half that, and so on and so on. In our case, you can think of the different types of notes as allowing you to define not only when the note takes place, but for how long of a gap you're going to have before you get another note. So in the case of, say, A quarter note, which gets one full beat, if you considered all of this to be one beat, a quarter note would probably take place, say, right here. So this would be a quarter note, and then you just have open range in between all this.
Exactly. If you were counting units in terms of a quarter note,
Right.
that means you'd have to go another quarter note before you would add in additional notes.
Exactly. If you were doing, what's half of a quarter note? Eighth note. So let me try to draw an eighth note and not embarrass myself. So boom, and then they do something like this. They got the little flag. So an eighth note would actually hold off for half of this beat. And then the other half would be open to play, say, another eighth note if you were so inclined.
Another way you could say that is you could fit twice as many eighth notes in the same amount of space that you'd fit any given number of quarter notes.
Right, and 4 times as many 16th notes, and so on and so on. Now, because of this, it's going to help us a great deal conceptually if we can go ahead and lock down the number of calculations that can take place per note.
Exactly, because going back to the whole problem of having to quantify everything into discrete units, the problem we run into is if we keep dividing, we can go on into infinity.
Exactly.
So we need to decide where the road ends. What is the finest note, the smallest note, or quickest note that we can represent?
We need some way. Well, since notes are kind of the building blocks of music, and we're still trying to set up our time system, it makes sense to go ahead and assign them some concrete values. Now, here's how we're going to do that. We're going to start off, just in this particular example, just by discussing the quarter note. It is probably one of the more common notes you're going to run across. 4/4 time is dependent on the quarter note. It's 4 beats to the measure, and a quarter note gets 1 beat. That's the most common time signature, and it directly references the quarter note. So that's who we're going to put a huge amount of importance on. And this quarter note, we are going to set to a value of 96. What do you want to call them?
You just call them ticks.
Ticks. You can call them all sorts of stuff. You call them calculations, updates, and all sorts of different things. We'll call them ticks. 1 quarter note is going to be equal to 96 ticks. Now, why do we pick on 96? It's not really a magic number. It's 2 primary reasons. One is it's divisible by 2 and it's divisible by 3. The importance of 3 is so that if we wanted to, you could play a triplet. Now, I'm not going to go into all the musical theory behind it. If you want to know what a triplet is, I think if you Google it, you'll bring up a Wikipedia page to learn how to play them. But in short, it's just swapping out 3 notes in the place of 1. So and that would be.
But in order to swap those out and still equally place them, it would be very beneficial to be able to divide by 3.
That's right, because everything in the computer's got to be quantifiable. Now, the division by 2 is actually even more important because all of the different types of notes derive from each other in factors or multiples of 2.
Exactly. One way you could look at it is you could get from one note to any other note simply as a matter of multiplying or dividing from whatever current note value you're sitting at.
That's right. So here's a half note. Now, a half note is twice as long as a quarter note, so this is actually going to get a value of, 192 ticks?
Exactly. In order to make the passage of a half note take more time, it will take more ticks.
And a whole note, isn't that 256? Can I still add these
I think
together?
that'd be 380. 384.
384. I can add this stuff. No, I'm terrible at this kind of stuff, guys. So don't snicker too much. So now we've gone from quarter all the way up to a whole. Now if we go down the other direction, so let's make an eighth note. And so here's my shiny, awesome eighth note. This is going to be equal to, was it 48?
Exactly, 48.
48 ticks. I have notes. I'm just not looking at it. Isn't that great? And then we go down from there to a 16th note, which would end up being 24. I don't even know how to draw a 16th note off the top of my head.
It just ends up being more and more flags.
Yeah, that's right. And so we do, and isn't it like 2?
And then 2 on the 16th note. So yes, that's correct.
Yeah, okay. And then this becomes 24, and I'm going to quit drawing now.
So on and so forth.
So forth, yeah. And then really the key is that by the time you get down to a 128th note, you'd be down to 3, I think.
Exactly.
Yeah.
And at that point, you can't divide that in half anymore. Not evenly anymore.
Right, but see, also, we're assuming that a 128th note is as fast as you'd ever want to play.
And so if you're looking at this in terms of resolution, At that point, that's where you've hit the bottom. That's
Exactly.
why the 128th note is the shortest note that can be represented, because that's the smallest one that we can reach by even integer division.
Right. So if you were wanting to develop a system for some reason that went from a 128th note to a 256th note,
Well, it'd be mathematically be simple.
yeah,
Just double your
you'd have
tick
to
rate.
slide everything over.
Yeah, just double your tick rate, and that'll give you one more level of division.
What we're getting at here, though, is that we're probably never going to use a 128th note, probably. But we've got the ability to, and we're imagining that that's as far down as we'd ever want to go.
Now, another way to look at it is from the standpoint of a game. Are we really going to want to force our poor players to play anything faster than a 128th note?
Exactly. Even if you've got a really slow rhythm, like let's say 1 beat a second, cramming in 128 notes into 1 second is more than I can play. I mean, even doing a drum roll, that's more than I can get in a good drum roll.
So really, this is just a sane range to put together normal music within the context of a game.
All right, so with that, we've kind of walked you through all the directions we're going to go here. We're going to build the music engine, which is going to be an event-driven system that just so happens is going to leverage our sound engine to make noise. It's going to be familiar with time. It's going to be aware of notes. Because of that, it's going to be able to play rhythm. And there's the whole crux of a drum system right there. It's going to be able to play back some drum loops for us. We're going to talk about, during the course of this project, the idea of storing our notes for playback later. And then we talked a bit about time and how time musically is this really loose thing that's kind of abstract and can be very difficult to wrap your head around if you're not musically inclined. But we've got to take that and bring it into some quantifiable system that works with a computer, something that has discrete units. So that's what we've done here. By taking our tempo and breaking it up into the number of beats per minute and the number of ticks for each individual beat. And by increasing that number of ticks in between each beat, we have a higher resolution, a higher division that we can use to place notes in between each beat. And then we talked a little bit more about that and how that actually is going to lend itself over to how we're going to calculate notes, because we're going to take the different types of notes and simply assign them to a certain number of ticks. Because since we have a non-duration style system, I guess technically even if you did, really that type of note just defines when the note's going to play and then how much time you have between when the next note could play.
Or you could look at it from the other direction, that is, since we have assigned specific tick values to certain notes,
Yeah.
that means if you were looking at 96 ticks of empty space between notes, then you could infer that those notes were actually quarter notes.
Yeah, you could.
Or rather, if you needed to place a series of quarter notes, you would know ahead of time that you have to space those by 96 ticks.
And that's actually a really interesting point, too, because if we've decided that 96 ticks is a quarter note, which we have, that's concrete, and then we come up here to our ticks per beat, and we set that to also equal 96.
Ooh, that finishes off your concept of time signature.
Yeah, then you've technically got at least the lower half of 4/4 time, where you've already decided that a quarter note, which is 96 ticks, gets 1 beat.
Very nice.
Now, at the same time, you could go back and forth about the first part of it, of your, like how many notes per measure. In the grand scheme of things, we don't really care how many notes are going per measure. But that's a whole different discussion that I'm not going to get into right here. So I think with that, we've introduced you to all of the primary concepts that you're going to need to know to get into the music engine. So now from here on, we're just going to go ahead and start coding, and I'm excited. This should be kind of fun. So that'll wrap up this video. Thanks a lot.